Bismillah ar-Rahman ar-Rahim. In this video, we will discuss the AC circuit analysis with mutual inductance and how to use the dot convention in this case. Any wire, even a straight wire, having AC or DC current passing through it, would have a magnetic field around the wire. This magnetic field can be weakened, can be diminished, for example, in the case of a twisted pair. If we use a twisted pair like for electricity in the houses, the two twisted pairs or the twisted pairs would have one wire with current flowing in one direction, the other wire having the current passing or flowing in the other direction. The two magnetic fields resulting will cancel each other. Or we can strengthen the magnetic field, like when we have the straight wire in form of a coil, so that the magnetic field generated around each turn of the coil will add to the magnetic field around the other turn, and the overall magnetic field will be of considerable strength. When the AC or the current generating this magnetic field is alternating, then the magnetic field itself would be alternating, meaning it's changing with time. And in turn, the presence of the coil in the changing magnetic field will cause a current to flow through the coil, meaning a voltage or EMF has been generated on the two terminals of the coil because of the magnetic field, not because of the original current. The AC current passes through the coil, generating a changing magnetic field around the coil. The coil is an electrical wire present in a changing magnetic field. An EMF or a voltage difference will be generated on the two terminals of the coil because of the magnetic field. This generated voltage or EMF on the terminals of the coil because of the magnetic field will oppose the changing on the original current. Like, for example, if the current is following a sinusoidal wave like the graph we have, so when the current is increasing in the first quarter of the wave, the EMF generated on the coil will be such that it opposes this increment in the current in the form of impedance. The polarity on the coil in that case will be like it is positive here and negative here to oppose the original voltage source, like two batteries opposing each other in this form. Here is a positive, here is the positive, like it's an impedance opposing the original current or the current flow in the circuit. So that in this case, if we apply Kirchhoff's voltage law, the only voltage rise in the circuit would be the voltage source. So it will be V equals IR plus LI dI by dt, because the voltage generated around the coil or on the terminals of the coil because of the magnetic field equals minus L, V over on L equals minus L dI by dt. L is the inductance of the coil, dI by dt is the rate of the change of the current. The negative signs, as we said, always the generated voltage around the terminals opposing the change in the current. Here the current is increasing, so the voltage on the coil would be a voltage drop opposing the current, like the R opposing the current. When the current is decreasing in the next quarter of the wave, then the polarity on the coil would be reversed. It will be positive and negative like this, so that the voltage on the terminals of the coil would be like an additional battery added to the original voltage source. It would be like adding the batteries together, and if we apply Kirchhoff's voltage law in this case, it would be V plus L di by dt equals IR, like both the voltage around the coil and the source, both of them are supplying the resistance R. Because of this behavior, the EMF generated on the terminals of the coil is called back EMF, meaning it opposes the original current, and that's why we have a negative sign in the formula of the voltage around the coil. Now, if we have a circuit where one coil is fed or supplied by AC current, L1 is supplied by AC current, a magnetic field would generate around L1, and the voltage drop on L1 due to this current would be minus L di by dt, and this is called self-induction. Self-induction is the phenomenon in which or by which a change in magnetic field is generated around a coil due to an AC current passing through the coil. This generated magnetic field, the changing one, would generate in turn a back EMF on the terminals of the coil. So the first coil having a current passing through it, it would have a magnetic field and it will have a back EMF due to self-inductance. Having L2 near L1, and if it's near enough to be exposed to the magnetic field on L1, will cause a current, an AC current, to flow through L2. This changing or alternating current in L2 would generate a second magnetic field around L2, which would pass through L1, generating a second current on L1 due to the magnetic field on L2. This is called the mutual inductance. The generation of current and hence a voltage drop on a coil because of the changing current passing through another coil. So on each coil there would be two back EMFs. The first one in L1 due to I, it's minus L di by dt. And because of the magnetic field generated on L2, it would be M di 2 by dt. And it's called this M1 2 because it's generated on L1 due to L2. Similarly, on L2, there will be a mutually induced back EMF due to the current I1. This would be M21, the generated voltage or back EMF on coil 2 due to coil 1. It would be M21 multiplied by di1 by dt, and since I2 is passing through L2, there will be another voltage drop around L2, which is defined by the self-inductance, and hence it would be minus L2 di2 by dt. The polarity of the mutually induced EMFs or voltages will depend on the physical winding of the coils. And there are two cases for this: an aiding connection case and an opposing connection case. In the aiding connection, like the example in front of us, we have two coils L1 and L2. The current I1 through L1 is with this direction, so that if we apply the right hand rule, we can see that the magnetic flux is directing downward. It is the red one. The current I2 through L2 having this direction, again if we apply the right hand rule, we can see that the blue line or the blue magnetic flux, it's directing upward on the right, meaning it has the same direction like the magnetic flux of L1. So the two back EMFs generated on L1 because of I1 and I2 would have the same polarity, meaning the self-induced EMF around on the terminals of L1 because of I1 would have the same polarity like the mutually induced back EMF generated around the terminals of L1 due to I2. And similarly, the two back EMFs generated on the terminals of L2 would be having the same polarity. The one self-induced by I2 and the mutually induced on L2 due to I1. This case is the aiding case. Aiding because both EMFs induced on both coils are aiding each other. They are in the same direction. The second case, the opposing case, is where, like we have here in this example, I1 having the same direction like before, so still the magnetic flux represented by the red line is directing downward. The current I2 have a reversed direction in this case. If we reapply the right-hand rule, we can see that the magnetic flux represented by the blue line would now be directing downwards. So the two magnetic fluxes have opposing direction. Because of that, the self-induced voltage around L1 due to I1 will have a different polarity or reverse polarity when compared to the voltage on L1 due to I2. And on L2, the self-induced voltage around L2 due to I2 would be reversed in polarity to the mutually induced voltage around L2 due to I1. If you call, for example, uh, the self-induced voltage on L1 due to I1, VL1, because of self-induction, it would have a reversed polarity when compared to VM1, the mutually induced voltage on L1 due to I2. That's why we have V1 equals minus M di2 by dt, and V2 equals minus M di by d1 by dt. The minus sign here to let us know that both EMFs, self and mutually induced, have opposing polarities. And I'm sorry, I forgot to say that as we said here, there is an M21 and M12, but in fact, M21 always equals M21, M12, and that's why it's easier to use M in the equations. And now if someone buys a transformer, no one will open it to see how the fluxes are directing or the currents flowing direction. That's why it was agreed to use the dot convention when analyzing AC circuit having mutual inductance. Like the two circuits we have. We have two circuits. The one in the left have a voltage source, resistance R1 and L1, coil L1. The other one have a voltage source V2, R2, and a coil L2. The presence of the dots means they are mutually coupled. There is a mutual inductance which generate back EMFs on each of them. To know if these two mutually coupled coils are having an aiding connection case or opposing connection case, we have to check the direction of the coil of the current entering and leaving the coil. If both currents flowing through the coils, like I1 here and I2, if both of them are entering the dot or leaving the dot at the same time, this means it is an aiding connection case. If one current enter the dot while the other current leaving the coil at the dot, this means it is an opposing connection case. Again, I have L1 and L2, and I have the dot convention like the figure shows. So I can see that I1 enters L1 at the dot, and I2 enters L2 at the dot. So both currents enter the coils at the dot. So this means an aiding connection case, which means that the self-induced EMF and the mutually induced EMF have the same polarity. So if I apply Kirchhoff's voltage law on the circuit to the left, I would have V1, which is the only voltage rise, equals I1 R1 plus L1 dI1 by dt. This is the self-induced voltage on L1 due to current I1, and it's a voltage drop. Now for the mutually induced voltage, since this is an aiding connection, both mutually induced and self-induced will have the same sign, same polarity. So the voltage around L1, because of the mutual inductance, because of I2, would be a voltage drop as well. So it has to be written as plus M di by dt. It have the same sign like the self-induced L1 di 1 by dt self-induced voltage. On the second circuit, we'll have as well V2, which is the only voltage rise, equals I2 R2, the voltage drop on the resistance, plus L2 di2 by dt. This is the self-induced voltage around L1 due to I2, which is a voltage drop. Since the case is an aiding connection case, so the mutually induced voltage around L2 due to I1 would be having the same polarity like the self-induced voltage, so it will be a voltage drop as well. It will be a positive sign in this equation. In the frequency domain, using phasors, V1 equals I1 R1 plus J omega L1 I1 plus J omega M I2. In the second circuit, V2 would equal I2 R2 plus J omega L2 I2 plus J omega M I1. Another example showing the opposing connection case. We will have a circuit to the left with a current I1 entering the coil L1 at the dot. In the second circuit, the current I2 leaves the coil L2 at the dot. The rule is that the currents I1 and I2 should enter the coil, both coils on the dot, or both leaving the coil at the dot. Here we have I1 entering the coil at the dot, while I2 leaving the coil at the dot. So this is an opposing connection case, meaning the mutual inductance voltages would have a reversed polarity when self-induced. Mathematically would be, if we apply Kirchhoff's voltage law to the circuit on the left, we would have V1 is a voltage rise, and we have two voltage drops, one on Z1 and one on L1. It would be minus I1 Z1 and minus I1 J omega L1. Since I1 is a common here, the sign in the brackets is changed to positive. If you multiply this negative by the positive, it would be negative. The voltage, the self-induced voltage around L1 is negative, so, and we have an opposing connection case, so the voltage, the mutually induced voltage around L1 due to I2 would be positive J omega M I2. Again, the voltages around the first circuit is V1 minus I1 Z1 minus J omega L1 I1. Since it's an opposing case, so the voltage drop, the mutually voltage drop around L1 due to I2 would have a different sign to the self-induced one. This is negative, this would be negative. The same applies to the second circuit. Here is an example. It would be making it much better to understand. We have two circuits, one to the left having a voltage source 12 and angle 0. We have a capacitor minus J4, an inductor L1 with impedance J5, a mutual impedance J3, and we have L2. In the second circuit, we have a resistance and a coil only. The assumed currents for analysis is I1 and I2, both are clockwise directed. When we analyze an AC circuit with mutual inductance, we can use a model. We can redraw the circuit after adding the mutually induced voltages. Here in the left circuit, we have a voltage drop around the capacitor and a voltage drop around the inductor L1. But due to the mutual inductance, there will be a mutually induced voltage around L1 due to L2. Then we have to check the dot convention. I have I1 entering the coil L1 at the dot, I2 leaving the coil L2 at the dot. So this is an opposing connection case. So the mutually induced voltage on L1, I'm sorry, would be with reverse polarity to the self-induced voltage around L1. So the current I1 is flowing in this direction. The L1 having a voltage drop, meaning this is positive, here is negative. Since Vm, the mutually induced voltage on L1, is in reverse polarity to the self-induced one, so it will have a reverse polarity here. This would be negative and this would be positive, meaning it's a voltage rise. If we apply Kirchhoff's voltage law to the circuit, I will have 12 and angle 0. Easier it's, or straightforward, it's 12, or easier it's 12, minus the voltage drop around the J4 capacitor, it's minus J4 I1, and then we have a voltage drop around L1, it's minus I1 J5, and then we have a voltage rise here, which is I2 multiplied by the impedance of the mutual inductance, impedance defined as J3, so it would be positive J3 I2. Because it's opposing connection case, the voltage drop, the mutually induced voltage, would have a different sign or opposite sign to the self-induced voltage. If we work on the expression here, we'll have 12 minus J I1 plus 3J plus 3J I2 equals 0. So 12 by 3J I2 equals J I1. We moved J I1 to the right hand side. We solve for I1 to get I1 equals minus J12 plus 3I2. We divided here by J. So it will be 12 by J. J will go to the numerator with a negative sign. It will be minus J12 plus 3I2. Again, we will repeat the modeling in the for the second circuit. We have a self-induction or self-induced voltage around L2. This would be a voltage drop. I2 is in clockwise directed, so it will be a voltage drop. Here will be positive, here will be negative. In addition to the self-induced voltage, due to I2, there is a mutually induced voltage because of I1 and L1. We have an opposing connection case, so the mutually induced voltage will be reversed in polarity with regard to the self-induced. So it will be here, it will be like, here is negative, here is positive, this is mutually induced voltage. If you apply Kirchhoff's law now, I have a voltage rise, Vm2, which is 3J I1, minus the voltage drop around L2, it is minus J6 I2, and the voltage drop around on the resistor, it's minus 12 I2, and this equals 0. This means that 3J I1 equals 6J I2 plus 12 I2. If we again solve for I1, dividing by 3J, we will have I1 equals 2I2 minus J4 I2. We have now I1 defined with equation 1 and 2. We can equal the right-hand side of both equations, giving us that J minus J12 plus 3I2 equals 2I2 minus J4 I2. Solve for I2, having I2 multiplied by 1 plus J4 equals J12. So I2 equals J12 divided by 1 plus J4, transforming or converting the denominator into the polar form, having 4.123 and angle 75.96. The J can be converted to an angle of 90 degrees. So I2 equals 12 and angle 90 divided by 4.41 and angle 75.96, meaning I2 equals 2.91 and angle 14.04. We can get now the value of I1 by substituting I2. I1 equals 2 minus J4 multiplied by I2 equals, if we convert 2 minus J4 to the polar form, we'll have 4.47 and an angle minus 63.4 multiplied by I2 2.91 and an angle 14.04, meaning I1 equals 13.01 and an angle minus 49 dot or 0.39. A second example, which is interesting indeed, we have one circuit with one voltage source having two mutually coupled coils. L1, let's call them L1 and L2. L1 is J6 ohms, J2 is L2 is J8 ohms, and the mutual inductance value is J2. Again, we need to use the modeling to redraw the circuit. There are two meshes in the circuit. For mesh 1, we have the coil L1 having two currents passing through it. So if we analyzing mesh 1, I will have a voltage drop around, or I'm sorry, a reactive impedance around L1 equals I1 minus I2 multiplied by J6. It is I1 minus I2 multiplied by J6. And the presence of J2 and having I2 passing through L2, I'm sorry, we have I2 passing through L2. So this would generate a mutual inductance voltage around L1. Because of that, we have to check the polarity or the dot convention. We're having I1 entering L1 at the dot and I2 leaving the dot, leaving L2 at the dot. So in this case, in mesh 1, it is an opposing connection case, meaning that the mutually induced voltage around L1 because of I2 passing through L2 would be with reverse polarity to the voltage drop around L1. So if we redraw the mesh 1, we'd have the voltage source 100 and angle of 0. We have the resistance 4 ohm. We have the capacitor minus J3, and we have the voltage drop around L1. This would be because I1 is clockwise, so it would be here a positive sign and a negative sign here. Now, as we said here, I1 the voltage drop around J6 or L1, it's I1 minus I2 multiplied by J6. So the voltage drop due to I2 passing through J6 would be J6 multiplied by I2, but it has a different polarity. It will be like here is positive, negative, and here is positive. This is not a mutual inductive or mutually induced voltage. This is the voltage drop around the voltage drop around L1 due to I2. Now, for the mutually induced voltage around L1, it would be positive J2 I2 with this polarity. It's a voltage rise because it's an opposing connection case, meaning that the mutually induced voltage having a different polarity than the self-induced voltage. Here it's a voltage drop, here it must be a voltage rise. If we now apply Kirchhoff's voltage law to the circuit, we will have 100, we ignore the zero, the angle, 100 minus the drop on the resistance, 4 1 by minus 4 I1, and we have the voltage drop around the capacitor, so it will be minus J3 by I1 multiplied by I1. And then we have the voltage drop on the L1, which is not minus J6 I1. And then we have two voltage rises, J6 I2 and J2 I2. This would be simplified to AJ I2 minus I1 multiplied by 4 plus J2 minus 100 equals 0. This means that 100 equals 4 plus J3 I1 minus 8J I2 or J8 I2. In the same way, but it's more complicated to be honest. In the second mesh, we have a current I2 and we have three elements, a resistor and two coils. So I2 passing through the resistor and two coils would have three voltage drops. Voltage drop on R, voltage drop on J, on L1, and voltage drop on L2. And similar to mesh 1, the coil L1 having two currents passing through it. So there is a voltage drop due to I2 and another one due to I1. In other words, the voltage drop around J6 or L1 in mesh 2, it would equal I2 minus I1 multiplied by J6. So we have three voltage drops, one on the resistor, two on L1, one because of I2 minus I1, and then another voltage drop around L2 because of I2. Then we have a mutual inductance voltage voltage induced, mutually induced on L1 because of I2 passing through L2. And we have two mutually induced voltages around L2, one because of I2 passing through L1 and one because of I1 passing through L1. So if we redraw the circuit with the new model, we're having the circuit, we're having I2 in the clockwise direction. The first thing I2 would pass through is the coil. There will be a voltage drop. It would be a positive here and a negative here. Then again, there is a negative sign, I2 minus I1. So the voltage drop on on L1 because of I1 would be as a voltage drop. It will be here negative and here positive. Now for the mutual inductance, we have to check the currents. I2 leaving, we have two currents, so we have to consider each current separately. I have I2 leaving L1 at the dot and leaving L2 at the dot, so this is a mutual, it's an aiding connection case, meaning that the mutually induced voltage around L1 because of I2 passing through L2 would be having the same polarity like the self-induced voltage. Here is voltage drop, here must be a voltage drop with positive here and negative here. Then I2 would pass through L2 causing a voltage drop, positive here, negative here. And then as we said, it is an aiding connection with regard to I2 passing through L1 and L2. So the mutually induced voltage on L2 because of L1, because of Li2 passing through L1, it would be like positive here and negative here. It's an aiding connection. So this voltage having the same polarity like this voltage drop. And then we have an I1 passing through L1. It's entering the coil at the dot. I2 is leaving the coil at the dot. So it's an opposing connection. So it would be here having a reverse polarity to the voltage drop around L2. This means that it's negative here and positive here. This represents all the voltage drops with the resistor, of course. Now we can apply a voltage, Kirchhoff's voltage law. We have starting from the resistor minus 5 I2, and here is a voltage drop minus 6 J6 I2. Here is a voltage rise plus J6 I1 because it's caused by I1, minus here it's a voltage drop minus J2 I2, a voltage drop minus J8 I2, a voltage drop minus J2I2, a voltage rise plus J2I1 equal 0. This can be simplified to J8I1 minus 5J18 I2 equal 0. This is equation number 2 and this equation number 1, but I think it's better to use the matrices. We will define the coefficient matrix for I1 and I2. This would be 4 plus J3 from here. This is the coefficient of I1, and J8 from here. Likewise, it's J8 here minus 5 plus J18, and this is the vector for the variables I1 and I2, and this is the right hand side 100 and 0. I'm sorry for the mistake. Now we can find the determinant, the coefficient determinant. Delta equals the value of this, which equals 30 plus J87. Then we replace the first column with the right hand side values 100 and 0. We get delta 1 equals 100 multiplied by 5 plus J18, which means 500s plus J1800s. And we then get delta 2, replacing the second column of I2, of coefficients of I2 with the right hand side, 100 and 0. We get J18, 800, I'm sorry. So I1 would be delta 1 by delta. If we convert the right hand side here into the polar form, it would be 18680.2 and angle 74.5. And similarly, we can convert delta into the polar form, 92.03 and an angle 71. This means I1 equals 20.3 and angle 3.5 amperes. I2 equals delta 2 by delta equals 800 and angles 90 divided by 92.03 and an angle of 71 equals 8.7 almost, and an angle of 19 amperes. I hope the video is clear. I know the topic is a bit complicated. That's why I did record the video. I really hope it helps. Thank you very much. Assalamu alaikum.